transition a little bit now into some statistics. We're going to need some calculus in this unit, not immediately, but we're going to use some calculus in this unit to determine some things with statistics. But to start with, we're going to start with some discrete random variables. A random variable, you can read this, just some notes here. Really, the key piece here is we first of all, in chapter 23, we talk about discrete random variables. Chapter 24, we talk about continuous random variables, and we do some things with those. But we also need to remember all of our other things like our mean, median, mode, standard deviation. Those are also going to be very important, variance, and so on. So if you don't remember those, review those. Go look back in your notes and review standard deviation, variance, mean, median, mode. Those things shouldn't be an issue if you go back and review. To determine the value of a continuous random variable, we need to measure. So discrete random variables, we're counting. With continuous random variables, we measure them. So there is a difference. Okay? Continuous random variables we'll spend more time on in chapter 24. Same unit but different chapter. For a random variable, there's a corresponding probability distribution. So this is the probability distribution of the number of heads I can get when I roll a dice twice, or sorry, flip a coin twice. I could get 0 heads, I could get 1 head, or I could get 2 heads if I'm flipping 2 coins. Okay, if I'm flipping 2 coins, and really all it is showing up that I could get a tail and a tail, a head and a tail, a tail and a head, and a head and a head. So this is when it has 2 heads, this is 1 head, this is 1 head, this is 0 heads. There's 1/4 of those, 2/4 here, and 1/4 here. So that's the probability distribution. Okay? That one goes there, that one goes there, that one goes there. Probability distribution. Probability of getting 0 heads, 1 head, 2 heads. Same thing with the next one. It's just another example, except that's a column graph showing that. Okay? Discrete random variables. Being able to count the outcomes. So here, a supermarket checkout has 3 points, A, B, and C. The government inspector checks the accuracy, okay, and so on. List the possible outcomes. So they could be no, no, no. They're not accurate. Or it could be yes, no, 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 yes, no, 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 yes. So there's one that has all no's. There are 3 that have 1 yes. It could be yes, yes, no, yes, no, yes, or no, yes, yes. And again, there's 3 of those possible outcomes, and then yes, yes, yes. There's only 1 of those. So these are the possible outcomes. This is part A. Part B, describe using X the events of there being 1 accurate scale. So if X equals 1, okay, that would be 1 accurate scale. Part 2, double I, at least 1 accurate scale. So X could be 1, 2, or 3. Could be any of those. All right, continuing. Discrete probability distributions. Remember, probability always has to add up to be 1. So that's what this is saying. The sum of the probabilities from 1 to n is equal to 1. In other words, they all add up to be 1. Probability distributions can be done in 3 forms: table form, graphical form, and then also in function form, which we already showed with a probability mass function, P of x. So we'll talk about that as well. So a magazine store recorded the number of magazines purchased by its customers in a week. 23% purchased 1 magazine, and so on. What is the random variable? Well, the random variable is the number of magazines sold. Number of mags sold or purchased. Okay. So what are the possibilities? Well, it could be 0, 1, 2, 3, 4, 5. Is that all inclusive? Does that add up to be 100%? If I add those up, 23, 38, 21, 13, and 5. Okay. So So is it possible to have a 0? Could they have had 0? No. So it would be x would equal 1 through 5. Make a probability table. So we're going to make a probability table. This is for part B. 5, 4, 3, 2, 1. And then this is x, and this is the probability x equals that number. And for 1, it would be 0.23, 0.38, 0.21, 0.13, and 0.05. And then lastly, it's asking us to do a graph. So we can still do a graph as well. Let's just say this is 0.4, 0.1, 0.2, 0.3. And we can graph these, let's see, 1, 2, 3, 5. And this first one, 5% is going to be that column, that bar. And the next one is 13%, so it's a little higher. That's 4, 21% is 3, 38% is 2, so almost all the way to 0.4, and 0.23. It's a little taller. So there you go. That's a graphical representation. Continuing. If a bag contains 4 blue marbles and 3 red marbles, 2 marbles were randomly selected without replacement. X denotes the number of reds selected. Find the probability distribution of X. So here, let's show this first of all by a tree diagram. We're going to select 2 marbles. And we have red and blue. And it's without replacement, so in other words, dependent. Red and blue, red and blue. And if I multiply those, let's see, this is 4, 6, 2, 6. And over here, it's going to be 3/5, 2/5, because it's compound, or it's compound probability or dependent probability. So here I get a red and a red, so that means X is 2. Here I get a red and a blue, so X is 1. Here I get a blue and a red, so X is 1. And here I get a blue and blue, so X is 0. Okay. To do the probability distribution, we can simply look at a table. Probability X is the X value here. So let's see, 0, 1, 2. Okay, 0, 1, 2. Let's see. Of getting these, I would simply have to multiply. So for getting here, 2 6 times 1/5 is 2/30 or 1/15. 2/30. That's probably of getting 0. Probability of getting 2 would be 12/30 by simply multiplying that times that, and whatever's left, that's 16/30 is left over, because it has to add up to be 1. So that's the probability distribution of that. All right, continuing, we're going to move on here. Expectation, the expected outcome. Expected outcome, if there are n trials of an experiment and the event has a probability of p of occurring in each of the trials, the number of trials we expect the event to occur is n times p. Then also the expected outcome, E of x is equal to the sum, is equal to mu, or it's equal to the sum of n from the terms to n of each term times its probability. Each term times its probability. So an example, each time a footballer kicks a goal, he has a 3/4 chance of being successful. In a particular game, he has 12 kicks for a goal. How many goals should you expect him to kick? All it simply is for this problem, it's 3/4 times 12, or in other words, 8 goals if he kicks it 12 times. Pretty basic idea there. With fair games, talking about fair games, in gambling, we say that it's the expected gain of a player from each player is the expected return or payout from the game. The game will be fair if the expected gain is 0, meaning neither gain or loss, the casino doesn't make money and the player doesn't make money. It's even, it's 0. So then it's considered a fair game. Now, remember, if you go to a casino, it's not fair. The casino is going to win more often than the player. That's how Las Vegas survived and how Las Vegas grew, is because people gamble and it's not a fair. The games are not fair. And we can determine whether a game is fair mathematically. And here's an example. In a game of chance, a player spins a spinner labeled 1, 2, 3, 4. The player wins the amount of money shown in the table depending on which number comes up. Determine the expected return for one spin of the spinner. So in doing so, all I would need to do is the expected value of y. Let's move over here. The expected value of y is 1/4 times 1 plus 1/4 times 2 plus 1/4 times 5 plus 1/4 times 4, if they are all equal. If the spinner has equal space for those, that would be the expected outcome. So the expected outcome is $4 if I add all that up. Okay. Now, so if the casino is charging $4 to play this game, it works out just fine. It's a fair game. But let's say the casino is charging $5 to play the game. Then it's the casino is going to make $1 on average on every spin. Okay, so it's a fair game, but the casino is going to make money. Yes, you have a chance of getting your money back and a chance of making $3, but most of the time you also have a chance of losing your money. Okay, so the expected gain of the player, if it is cost to play $5 each game, the expected gain is -1. So because if it costs $5 to play it, 4 minus 5, the expected value minus what it costs, gives us the casino $1 every time. Okay, and then lastly, whether you would recommend playing this game. If the expected outcome is not equal to 0 or is not positive in your favor, don't recommend playing it. So part B and then part C, if the expected value of y is not equal to 0, it's not fair. So don't play that game. Pretty simple idea for expected value. That's it.